I'm Daniel Palanker. I'm associate professor in the Department of Ophthalmology and in Hansen Experimental Physics Lab at Stanford. I work on optical and electronic technologies for ophthalmic care, which include lasers for retina, glaucoma therapy, cataract surgery, therapy for dry eye that I'm working currently on, and retinal implants and neural stimulation in general, in particular retinal prosthesis. The most recent example of the technology that is becoming clinical reality is a femtosecond OCT-guided cataract surgical system that we developed also starting in 2005. It was commercialized later in 2011. And now there are already 4 competitors that came up with a system basically replicating what we did, OCT-guided femtosecond cataract surgery. It is a field probably which will be the largest, or one of the largest fields of application of lasers in ophthalmology, because cataract surgery is so prevalent. It's about 30% of population will undergo it through the life cycle, about 3 million procedures a year just in US alone. And this market, if penetration will be deep enough, will become larger than refractive surgery, which was the largest laser market. What is interesting that the demand for the specific lasers that can perform this type of surgery, femtosecond lasers with tens of microjoules in energy and 100 kHz rep rate, did not exist. So demand was created by our development, and it created a new market where now several manufacturers suppliers of these lasers that didn't exist before the need was actually created, and this became a big boost for the whole femtosecond laser technology in general. So this shows the dynamics that good applications actually create a whole niche of suppliers, not just the builders of an end product, but OEM suppliers, and it becomes a large industry. Traditional cataract surgery, manual surgery, is limited in precision by surgical skills and by limited visibility of the tissue. Not always the lens capsule is well visible, and this affects eventually precision of positioning of intraocular lens and refractive correction. With femtosecond laser, cataract surgery can be executed by prescription, so it will be perfectly centered. The size of the opening in the lens capsule, capsulotomy, will be precisely determined with a precision of cellular scale, literally. Orders of magnitude more precise than human hand can actually do it. And without human error. So this procedure, and that's probably the most important component, that any surgeon now can do cataract surgery as precisely as the best surgeons, and even better, could do today. Retinal prosthesis is probably the most complex project I currently develop in my lab. It is both complex photonics and complex electroneural interface, which makes it very interesting and challenging. The idea of restoring sight with electrical stimulation is not new. It was proposed in the 90s by Robert Greenberg and Mark Humayun and John Hopkins. And the current approaches, or the approaches I saw with wired implants, that information is delivered with radio frequency and then converted into electrical signals and delivered to retina with wired cables, just didn't look right to me. And because of my optical background, I thought that we should do it optically. And we came up with the idea of photovoltaic approach, where the implant is very simple photovoltaic array, no wires attached, just basically replace photoreceptors with photovoltaic cells in a niche. And in a nutshell. And then everything else is done by goggles. So you wear video goggles, information is delivered optically to the eye with a pulsed near-infrared light. All the implant does is converts pulsed light into pulsed current, and it stimulates neurons. So this is an approach which was developed because of my background in optics and ophthalmology. It was very natural for me to think along the lines of optical activation. And this is a very appealing approach to surgeons because the implantation is very simple. It's just injection into subretinal space, some small modules of this arrays, and we can tile large area by multiple modules, and everything else is done by goggles. But goggles like that don't exist, so we also work on development of pulse near-infrared goggles with high enough brightness. And by the way, the same version of goggles with visible light will be used for optogenetic activation of the retina. It's another approach for restoration of sight. They also need very bright pulsed light on the invisible part of the spectrum. So this product of goggles for activation of artificial sight is dual purpose. In terms of goggles, since Google commercialized or popularized the concept of visual goggles with their Google Glass, it's very easy for us to explain now what we are doing. We can just say that it's a Google Glass for the blind. In terms of what is left to be done, in terms of technology, it's encapsulation of our implants into a durable coating that will survive at least 10 years. That's FDA requirement. We didn't have to do it for animals, but we have to do it for humans, and it's a process and fabrications that we are now ironing out. And we have to build a compact, sleek and powerful goggles that patients can wear. Again, we didn't have to do it for animals. We could just project from a slit lamp, but for humans we have to go that route, and that's what we are planning on doing now. And for me, it's very important to see happy patient, happy physician. But it's not every project has to go that far. Only the best projects are actually getting to clinical practice. Some laser tissue interactions or electroneural interfaces that we study don't materialize in a specific product. They become maybe a foundation and knowledge that help us to develop products later. So I don't expect from every product and every project and every graduate student a product that will go out into the market, but overall the expectation is, yes, to solve problems and to see the end user in healthcare. Applications or unmet needs pop up here and there in discussions, and so because it's always on the back of your mind what you can do, then suddenly you realize that this is a solvable problem and it can be addressed this way or that way. But it's not that I am actively looking every day what to do with the tools I have.